Hello students, welcome to fifth lecture of S block elements. So we completed the first part of our unit group 1 elements, and now we are moving towards the group 2 elements alkaline earth metals. So group 2 earth metals comprise beryllium, magnesium, cesium, strontium, barium and radium. They follow alkali metals in the periodic table, and these are the known as alkaline earth metals except beryllium. The first element, beryllium, differs from the rest of the members and shows diagonal relationship to the aluminium. The atomic and physical properties of the alkaline earth metals are as shown table 10.2. So note here the first element, beryllium, again shows different behavior than the rest of the group member as we discussed in previous case. That means first member of the group for group 1 element was lithium, and it was different from the rest of the member. And the similar situation is going on here. So first of all, we have electronic configuration. So this group has also same type of electronic configuration just like the first group, but difference is it contains 2 electrons in s orbital. So their common electronic configuration will be noble gas core Ns2. Like alkali metals, the compound of these metals are also predominantly ionic. That means you will get ionic compound from the nature for these metals as well, because they are again reactive just like first group. In this table we have elements with their symbols and electronic configuration. So as we can see, we have noble gas cores in each of these elements. Here we have 1s2, that means it has helium core. Then we have 1s2 to 2p6, that means neon. Then we have 1s2 to 3p6, that means argon core. Then 1s2 to 4p6, that means krypton. Then we have 1s2 to 5p6, that means xenon. And lastly we have radon. And the last element of this group is radioactive. It is known as radium, one of the very well known radioactive element, radium. So radium contains radon core and extra 2 electrons. Now atomic and ionic radii of this group. So atomic and ionic radii of the alkaline earth metals are smaller than those of the alkali metals. And reason for that is we are moving towards the left to right, that means nuclear charge is increasing. So electron feels stronger attraction towards the nucleus, and that's why sizes shrink. So within this group the atomic and ionic radii increases with increasing atomic number. So increasing atomic number, that means we are moving from top to bottom. And as we can see in the electronic configurations, with increasing atomic number, outermost orbits are also increasing. In first element we have second orbit as outermost, then for second it is 3s, for third element it is 4s, for fourth it is fifth orbital, for fifth element it is sixth, and for sixth element it is seventh. So as we are moving from top to bottom, each and every time a new orbital is forming around the nucleus, and that's why sizes are increasing. Next is ionization enthalpies. The alkaline earth metals have low ionization enthalpies due to the fairly large size of their atoms. Since the atomic size increases down to the group, their ionization enthalpy decreases. Now keep in mind, ionization enthalpies are always positive. That means removal of electron always requires energy. So that means lower the value of the ionization enthalpy, easier will be reaction. You won't get negative values for ionization enthalpies even for these type of strong metallic ions. If normal tendency of element is to lose ions, still it requires energy. So that's why, as mentioned, these elements are easily ionizable. That means they can release the electrons easily, but still we need to put some energy for that. And as we move from top to bottom, sizes are increasing, and with increasing sizes, distance from the nucleuses are increasing. Suppose this is our nucleus and this is the first element. So outermost orbital electron in distance is quite small. Then next element will have one more orbital, that's why distance increasing. and when we reach to the last element, you will reach up to 7th orbital, and that's why distance of the electron, outermost electron from the nucleus is fairly large, and that's why removal of electron becomes easy. And the values of their ionization enthalpies are mentioned in table 10.2. So here is the table, and as we can see, we have ionization enthalpies of the respective elements. As we can see, initial element have quite high value of ionization enthalpy. That means we need to put 899 kilojoules of energy per mole to ionize beryllium. But as we move from left to right, that means actually we are moving from top to bottom in periodic table. Ionization enthalpy values are decreasing. Now if we compare the ionization enthalpies of these metals with the previous metals, that means group 1, then these metals or alkaline earth metals have higher value of the ionization enthalpy. We are talking about the first ionization enthalpy. That means when we want to remove only one electron from group 1 and group 2 members, then we need to put more energy for group 2 members. So if you compare two adjacent elements, lithium and beryllium, then you will notice we have only one electron difference, but still removal of electron from the lithium is easy than the beryllium. And simple reason is because we have partially filled orbital in the lithium, which is comparatively less stable than the fully filled orbital present in beryllium. So each and every member of second group contains fully filled s orbital, and because of that these orbitals are quite stable. If orbitals are fully filled, then they are stable. So because of stability, removal of electron from fully filled s orbital is quite difficult, and that's why enthalpy values are also increased in group 2. So this is the reason why removal of first electron is difficult in second group than the first group. But if we check the second ionization enthalpy of both groups, that means group 1 and group 2, then enthalpies of alkaline earth metals are smaller than those of the corresponding alkali metals. Now reason for that is, let's talk about the ionization of first two elements of both group. So as we can see in first group element, that means lithium, initial electronic configuration was unstable. It was 2s1, so it is unstable electronic configuration. And later, after the ionization or removal of first electron, you will get 1s2. That means fully filled electronic configuration. So this electronic configuration is stable. So our change is unstable to stable for first group element. As we move from next element, as we can see, initially it has 1s2, 2s2, so it has stable electronic configuration. And when we remove the electron, you will get unstable electronic configuration. That means partially filled s orbital. So change is stable to unstable. Now keep in mind, whenever unstable to stable change occurs, this loses energy. That means this reaction requires least amount of energy, or these type of reactions can even generate the energy. That means exothermic reactions will occur. So these type of reactions are easiest one. Then next difficult reactions will be either unstable to unstable change or stable to stable change. These type of reactions requires some points of energy, or if they are exothermic, then they will lose comparatively less amount of energy than the first one. And then highest amount of energies are required when changes are stable to unstable. That means if initial states are stable and final states are unstable, these type of reactions always requires energy, and they are most difficult if we compare these three different categories. So easiest reactions are unstable to stable change, and hardest reactions are stable to unstable change. So if we check the lithium, first case for the lithium, then it is unstable to stable change. It follows in first category, which requires least amount of energy. And for beryllium, it is stable to unstable, which follow in last category, which requires highest amount of energy. But what about the second step or removal of second electron? Because we need second ionization enthalpy values to compare both of them. So when we remove one more electron from the lithium, then you may get lithium plus 2 ions. Usually these type of ions are highly unstable, so you won't see these type of compounds which has lithium plus 2 ions. But still, let's assume we removed one electron from lithium plus ion, then you will get 1s1 electronic configuration. As we know, this state was stable, in which we have 1s2 electronic configuration, and 1s1 configuration is unstable electronic configuration. So this change is stable to unstable. And let's check about the beryllium. When we remove one more electron from the beryllium, you will get Be2 plus, which has 1s2 electronic configuration because we removed one more electron from 2s1 orbital. So now 1s2 is comparatively stable because of fully filled s orbital. So this change is unstable to stable electronic configuration. So notice, on first removal of electron, lithium of reaction was unstable to stable, which requires least amount of energy, and reaction of the beryllium was stable to unstable, which requires highest amount of energy. But situation is flipped for second reaction. Second reaction changes stable to unstable for lithium, which requires least amount of highest amount of energy, and for beryllium it is unstable to stable change, which requires least amount of energy. So that's why first ionization enthalpies of alkali metals are comparatively low than the alkaline earth metal, and second ionization enthalpies of alkaline earth metals are low than the alkali earth metals. Next is hydration enthalpy. Like alkali metal ions, the hydration enthalpies of alkaline earth metal ions decreases with increase in ionic sizes. So Be2 plus has higher value than the Mg2 plus. Mg2 plus is higher than Ca2 plus. It is higher than Sr2 plus. It is higher than Ba2 plus. Now notice, reaction of radium are not mentioned if we compare with other elements, because it is radioactive element, and that's why it is less abundant and it is dangerous to work with. So we do not have much data about the radioactive element. The hydration enthalpy of alkaline earth metal ions are larger than those of alkali metals ion. Thus, compound of alkaline earth metals are more extensively hydrated than those of the alkali metals. Example, MgCl2 and CaCl2 exist as MgCl2 6H2O and CaCl2 6H2O. So in this case, we even use calcium compounds for moisture removal processes. Let's say in laboratory we need moisture free atmosphere. Then we will put calcium compounds, usually calcium hydroxides, in the container, and calcium hydroxide will absorb the moisture present in air because it has stronger attraction towards the hydrogens, water molecules. So group first members won't form such hydrates. Now let's talk about the physical properties. So alkaline earth metals in general are silvery white, lustrous and relatively soft but harder than the alkali metals. Now notice all of these group members have soft metals, group first and group second, because metallic bonds depends on number of valence electrons. So number of valence electrons in group 1 is 1 and group 2 it is 2. So because of very less number of electrons, their metallic bonds are comparatively weaker. And as the number of valence electrons increases, bonds become stronger. So these metals have comparatively less number of valence electrons, and that's why they are soft. But when we compare the first group with second group, first group contains only one electron, that's why they are softer than the group 2. Beryllium and magnesium appears to be somewhat grayish. The melting and boiling points of these metals are higher than those of corresponding alkali metals due to the smaller sizes, and the trend is however not the systematic. Because of the low ionization enthalpies, they are strongly electropositive in nature. The electropositive character increases down to the group from Be to Ba. Now similar reason, removal of electron becomes easy as the sizes increases, and because of increasing size, distance increases, and that's why removal of electron is easy and metallic nature is also increasing. Calcium, strontium and barium impart characteristic brick red, crimson red and apple green colors respectively to the flame. In the flame, the electrons are excited to the higher energy levels, and when they drop back to the ground state, energy is emitted in form of visible light. So just like first group member, these metals also exhibit color in visible region. When we heat this metal powder on flame, they will absorb the energy from the heat, and then electron gets excited. Electrons will shift in higher energy orbitals, then they will come back. So first they will absorb the energy, and by absorbance they will shift in higher energy orbitals. When they come back, they have to lose the energy, and they will lose energy in visible range. The electron in beryllium and magnesium are too strongly bonded to get excited by flame, and hence these elements do not impart any colors to the flame. The flame test of CaSr and Ba is helpful in their detection in qualitative analysis and estimation by flame photometry. Now, qualitative analysis practicals are also in our syllabus. Inorganic qualitative analysis practicals uses some of the metals mentioned here. And when we put the paste of these type of metal compounds on the flame, then flame color will be as mentioned here. Depends on the metal, depending on the metal, flame will give different type of colors, and we can identify given element from the color produced in flame. The alkaline earth metals, like those of alkali metals, have high electrical and thermal conductivities, which are typical characteristics of metal. From the next lecture, we will discuss about the chemical properties of these metals.